Hi everyone, it's good to see you here today. My name is Chen Yuhan, and I've been building iOS apps since iOS 7. In 2018, I joined the Line Corporation, where I've been working on various exciting features. Currently, I'm part of the Line app-based dev team, focusing on database solutions and optimization. Today, I'm excited to share the story of how we modernized Line's core data stack to a foundational component of our iOS app. As you know, Line has been around for over a decade, and some of our core data implementations were showing their age. In this session, I will walk you through the challenges and strategies we faced while migrating a decade-old core data stack to a modern architecture. You can also treat this as a core data lecture. Here's what we'll cover today. First, the background of the project. Then, a quick refresher on core data essentials. Next, we'll dive into the architecture options we explored, including the trade-offs of each. And finally, the strategies we used to develop and roll out the changes. Let's get started. First, why did we decide to refactor our core data architecture? Please take a look at this graph. It's a similar version of the core data stack we had used for our primary database, which stores chat and message data. If you are familiar with the core data, you'll recognize components like the context, coordinator, and store. If not, don't worry, we'll come back to this graph soon. For now, just note that this structure has become outdated and unnecessarily complex. Another big reason behind the refactoring is the related database code was still written in Objective-C. In fact, only 1.5% of Line's iOS code is still in Objective-C. But because of the importance and the complexity of this part, the implementation had remained untouched until now. This makes it harder to maintain and update, also difficult for new developers to understand. This refactoring gave us the perfect opportunity to migrate more logics to Swift. Now that we've covered the background, next, let's take a moment to go over some core data essentials. Just enough to give everyone a shared foundation before we dive in the architecture. Here's something I always like to emphasize. Core data is a framework, not a database, not a wrapper for SQLite. Because of this, core data has some unique features that you won't find in traditional databases. For example, one of the most important concepts in core data is the core data stack. Here's an example of a typical stack. This is the most basic and minimal setup. From this diagram, you can see that the core data stack is organized into 3 main layers. At the bottom, we have the underlying data store. In our case, it's SQLite, along with the NS persistent store class, which serves as the abstract layer for managing different types of store. At the top, we have NS managed object context and NS managed object, where we create, fetch, update, and delete data. It's a layer we interact with most in our daily development. In the middle, the persistent store coordinator acts as the bridge. It helps the contexts and the persistent stores communicate. Here's a detailed example of how the topmost layer in the core data stack handles saving data to the persistent store. First, we create a new instance of the book object within a specific context, and then simply call save on that context to persistent the data. In core data, there are generally 2 types of managed object contexts. One that runs on the main thread, called the main queue context, and one that runs on a background thread, known as the private queue context. It's common to use a background context for tasks like importing large data sets or things that could block UI if run on the main thread. At the same time, you might use main context for displaying data. Let's back to the stack again. Beyond the basic one, we can build countless different stacks if we want. For example, we can create a stack with the multiple coordinators, or multiple contexts on the same coordinator. After reviewing several core data stack types, you might be wondering, what are the differences between them? To answer this question, let's move on to the architectural options to compare the differences and evaluate the strengths and limitations of each. Let's start with the simplest stack design, a single coordinator and a single context. In this structure, all tasks are executed serially within that one context. So if a heavy operation is running, everything else has to wait. Now, if the context is a view context, heavy operations can easily block the UI. On the other hand, even if it's a background context, the potential performance bottleneck cannot be completely avoided, and we'll need to do extra work to safely interact with the UI. However, for small, simple apps where you don't need to handle complex tasks, this design can actually be the most suitable choice. What about more complex stack structures? Let's take a look at the case of using multiple coordinators first. Before diving in, we need to understand two concepts. The first is something called a row cache. Core data is a long-standing framework developed at a time when memory was expensive and devices were much slower. Because of this, caching played an important role in how core data managed resources efficiently. The row cache keeps a lightweight version of the most recently fetched or saved objects at the coordinator layer, so each coordinator maintains its own row cache. To understand how the row cache works, let's walk through the data fetch process. When fetching data, the application accesses an underlying store to retrieve the raw data. That data is then processed and returned as faults, not fully realized object. At the same time, the fetched data is stored in the row cache for future use. What is fault? If you are wondering that, perfect, since that's exactly what I'm about to talk. Faulting is a technique core data uses to manage memory efficiently. Think of it as lazy loading for managed objects. An object fault is a lightweight instance of the appropriate class. Its persistent data is loaded only when needed. For example, suppose we have an entity called book. When the object is still a fault, it contains only the object ID. Other attributes, like page count or title, remain in fault state, which means they are not loaded in the object until they are accessed. When we try to access a title attribute, the fault will be fired, and the actual data is retrieved. Core data first checks the row cache to say if the data is already there. Please say the blue line. If it finds a match, it uses the cache data. Only if there's no match, a cache miss, core data falls back to fetching the data from the underlying store. Retrieving data from the underlying store involves an I/O process, which can be costly. In contrast, using the row cache is much more efficient and less expensive, since the data is already in memory. So, the combination of faulting and the row cache helps core data balance memory usage and performance effectively. The second important concept here is merge conflict. Imagine a case where two different coordinators fetch the same data, but later save different changes to the store. When that happens, a conflict can occur because the same record has been updated in multiple places. I won't go too deep into this topic today, but here's a key point. Core data provides something called a merge policy, which allows it to automatically resolve these conflicts based on rules you define. In our example, we are using the override merge policy. We have talked quite a bit about the multiple coordinator structure, but you might wonder, why do we rarely see this structure in projects nowadays? Well, here's why. First, Apple changed the concurrency design of the NS persistent coordinator from iOS 10. Before, a coordinator could only establish one SQLite connection, no matter how many contexts were connected with it. This meant concurrent reads and writes were not possible unless we're using multiple coordinators. But after iOS 10, coordinator has a small connection pool that allows concurrent database operations. Generally, more coordinators means higher memory usage. And since we can benefit from the row cache when using multiple coordinators, we prefer to use a single coordinator in most cases. Another reason is, at the same time, Apple introduced a new high-level class, NS persistent container, which simplifies coordinator setup. By default, it uses only one coordinator, and is now the recommended and simplest way to build a core data stack. Next, let's take a closer look at another complex structure, multiple contexts. This is a completely different scenario. In this stack, several contexts share one coordinator, which means they can take advantage of the same row cache. Also, it's possible to run heavy tasks in the background context while keeping the UI responsive. Of course, since this is a structure that supports concurrency, merge conflicts can still happen. This time, it's between the context layer and the row cache. But we can handle them with a merge policy as well. Very easy. Sounds pretty ideal, doesn't it? Sadly, it's not. We didn't mention this earlier when discussing multiple coordinators, but actually, in any concurrent stack, we need to consider how to synchronize data between contexts. A common approach is to observe NS managed object context data save notification and manually merge changes to target context. Since iOS 10, core data provides a useful property called automatically merges changes from parent. When using independent contexts, this allows a context to automatically merge changes from its parent context or the coordinator. However, data sync isn't as easy as it sounds. Consider this example. We delete a book object in the background context and save that change to the persistent store. Before the sync completes, the same book object still exists in the view context. At this point, we are still able to fulfill the fault. So maybe we'll do this, but if we try to do this, the app may crash because the app object is no longer exists. In summary, this structure is quite effective. It's simple enough and it makes it easy to ensure that database operations don't block the UI. However, if we go with this approach, we need to be careful with the concurrency handling. Interestingly, we can also nest contexts. This is known as parent-child context structure. In this structure, changes made in the view context must go through the background context to be saved. Compared to the basic stack, we can move heavy tasks to a background thread, which helps reduce UI blocking, and compared to the independent context structure, no need to manage concurrency at all. That's a big plus. But of course, it's not without downsides. Even though data writing is pushed to the background, the view context can still block during heavy background operations. And there's an important thing we have to remember. When saving data from child to parent, the parent context data will always be overwritten. It completely ignores any merge policy you've set. So we have to be careful when using it as well. Both independent and parent-child context structures have their own pros and cons. So, what if we combine them into a hybrid structure? It sounds like a great idea, but in fact, it brings more problems than benefits. Firstly, we will lose key benefits of the independent context structure, like the clear separation between contexts. Also, we don't get the full advantages of the parent-child structure. We still have to handle concurrency. In short, it inherits downsides from both structures. But honestly, there's one specific situation where I think it might be useful. If for some reason you can't or don't want to enable automatically merge changes from parent, and you are working with many independent contexts, a root context might actually help. With this structure, by connecting all to the shared root context, when handling data sync, you only need to observe save notifications from the root context, instead of subscribing to notifications from every individual context, which simplifies data syncing and reduces boilerplate code. Now, here's a question. What is the best stack design? I believe there's no one-size-fits-all answer to this question. Instead, I'd like to ask, what kind of stack best fits our app? Now that we have explored the different stack types, it's clear the role each part plays in the original design. It used multiple coordinators and multiple contexts, even a hybrid context structure. This architecture was well suited to our needs, but in today's context, it feels unnecessarily complex. Let me ask you another question here. What solution are you considering to refactor the complex core data stack? Abandon core data, or just remove secondary coordinator, or change to use independent context structure, change to use parent-child context structure? Maybe you are thinking, let's just get rid of core data. Problem solved. But we love core data. It's a powerful tool. And consider the reality of the project. My answer would be remove secondary coordinator and change to use independent context structure. Here is our solution. Finally, we made this decision to use the independent context structure as our foundation because this structure is simpler, cleaner, and more flexible, while still keeping the benefits we needed for concurrency and performance. Based on this structure, we defined clear roles to each context, like keep the view context read-only, perform write operates always in background context. And for heavy or temporary tasks, we recommend using temporary contexts. Finally, we generally don't recommend creating long-lived background contexts, as they can introduce unexpected complexity and are harder to manage in the long term. Here, wait a minute. What about the potential crash risks with the independent context structure we mentioned before? Absolutely, we can't ignore this. I'll briefly introduce some commonly used strategies to help avoid running into such troubles, but I won't go into detail here. You can look into these approaches further after the session. To avoid and reduce potential crash, first, we should sync data as early as possible to keep the data out of sync window as short as possible. Second, we could use query generation when needed. It's a tool that guarantees a context won't say store changes until you tell it to do. Finally, we can also just use should delete inaccessible faults. Actually, this property is default to true, but if you want to rely on this, You must be confident in its behavior because it can lead to unexpected results. Here are some related links for further reading. So far, we have looked at several architectural options. The most important takeaway is to understand your needs and choose the one that fits your app best. Next, let's move on to something a bit more relaxed. I will share a few strategies we used during development and rollout. First, look at some code snippets that were frequently used in line project. Suppose the old stack is called stack, and we access view context and background context through its instance, like this. At first glance, you might think we need to replace every caller to use the new stack instance. And that sounds like a lot of work, right? Kind of like this. It's reasonable, but not what we are going to do. Imagine a scenario where we gradually replace the stack with new stack to reduce the risk of introducing a new architecture all at once. It sounds great in theory, but in practice, we want to avoid introducing an additional coordinator during the migration. Doing so could result in unexpected behavior. Also, if something goes wrong, it's harder to roll back all those scattered changes. So, we adopted a different strategy called branch by abstraction. It's a useful technique for tackling long-term refactoring. In our case, we introduced a new class. Let's just call it stack switcher here as an abstraction layer. It serves as a single entry point, deciding whether to use the legacy stack or the new stack. Both implementations conform to a shared protocol called Data Stack Protocol. This approach allows us to seamlessly switch implementations during development within minimal disruption to existing code base. And now, let's turn our attention to the use new stack value. Actually, it's also used for another strategy, feature flag. A feature flag is also a commonly used strategy. And in our case, we introduced two types. First, a compile time feature flag, configured via building settings. This allows us to include or exclude specific code during certain build phases, such as development, beta testing, or even targeting to specific app versions. The second type is a runtime feature flag, which is controlled by the server at runtime. It enables dynamic toggling based on certain conditions. Not just this project, the feature flag strategy is widely used across line projects. If you are interested in learning more, please check out our past presentations on this topic. Here are some links of these presentations. Let's back to the implementation again. As mentioned earlier, this refactoring is critical, and we want to minimize risk as much as possible. So we use the feature flags to roll out the change in two phases. In phase one, we focus on validating the switching logic only. In this phase, compile time feature flag was set to true, but the runtime feature flag remained false. This means we still use a legacy stack, but with the switching logic in place. In phase two, both flags were set to true. The new core data stack was fully enabled. Actually, fully enabled isn't quite accurate. In fact, we used a progressive release strategy to migrate to the new core data stack. Since the migration carried a significant risk, our goal was to make the rollout as safe as possible for our users. Instead of enabling the runtime feature flag for everyone at once, we roll out the change step by step, targeting specific regions and a controlled percentage of users. For example, starting with company-wide dog fooding, and then released to region A with only 50% of users, to region A with 100% of users, and so on. By taking this approach, we are able to monitor logs, catch issues early, and make improvements before a full rollout. We don't just use these strategies for this project. They are applied across multiple projects. Our goal is always to deliver a highly usable and stable experience to our users. That's my sharing. Thank you for listening. I hope you enjoyed this session and continue to enjoy using the Line app. Please feel free to come talk to me at the Ask Speaker corner. I also speak Chinese and Japanese. Thank you.